Welcome to a new episode of the Elevate Your Vision podcast, the podcast about producing everyday tools and prototypes for people with visual impairments. Today, I want to talk about my experiences with the 3D printing and making tools for visually impaired people. My name is Jürgen Hüllen, and I'm the host of this podcast. Since 30 years, I am working in the BFW Düren, which is a vocational training center for blind and visually impaired adult students in the far west of Germany. In our organization, we educate about 160 adult students. In addition to vocational training, we also provide the basic training content for people with visual impairments, like education of Braille, mobility training, and all-day living skills. For this, we also need tactile teaching materials. Until 2015, these were produced in our workshop using traditional manufacturing processes. A colleague who was a trained model maker and a mobility trainer was responsible for this. This extraordinary combination of skills allowed us to produce very good tactile models for all training areas and to adapt them to the individual needs of the course participants. However, a major disadvantage was that these were single unit productions that could only be reproduced and modified in a very time-consuming manner. To make matters worse, the colleague was about to retire. Thus, there was no longer an expert who could continue his work. There was also no indication that a member of staff with similar abilities would be able to be recruited. This resulted in the foreseeable problem of not being able to produce any tactile teaching and learning materials despite having a well-equipped workshop that was standing empty. For this reason, we decided early on to determine the opportunities that 3D printing offered for our needs. With the help of a partner company, we were shown practical examples of how additive manufacturing could be used for our purposes as early as 2011. However, the high costs of 3D printers and their print quality at this time were a deterrent. In 2016, the first FDM 3D printers were purchased by our organization. As head of the research and development department, I was responsible for this initial stage. Here, an important note about our decision. This was not a vote against classic manufacturing processes, but a reaction to the personal changes in the company. In fact, classic manufacturing processes offer a wider selection of manufacturing materials and the opportunity to produce larger parts. However, this requires having the appropriate machines and workshop, but in particular, appropriately qualified employees and staff members. Initially, the 3D printers were used primarily for tactile maps. In collaboration with mobility and ADL trainers, the necessary tactile materials were developed. The maps could now be produced in a manageable size that the mobility trainers or participants could carry. In the classic model making of thermoforming processes, this was not always possible because the materials had to be in a certain size so that they could be assembled. As time went on, ideas from the ADL trainers were also implemented. These included matrices for creating handwritten signatures or banknote identification. We also created different keyboards of cash dispensers to train blind students in using them and getting cash from the machines. The advantage of 3D printing is that designs can be changed relatively quickly using CAD software. improvements or changes can be implemented very quickly. Once designed, models can be easily adapted and reproduced. The increasing use of 3D printing also caused the facility management of our institute to ask us to produce spare parts for equipment and objects that were no longer available from the manufacturer. Another order was the production of tactile door signs with braille. So far, 3D printing is a quite usual service meanwhile in our institute for all our departments. Visitors of our company also brought us to the attention of municipal authorities and museums. This led us being commissioned by these organizations to produce tactile maps or door signs or tactile models to improve the accessibility of their buildings. An unusual example of this was an order for a biological exhibition. Here we were commissioned to digitally acquire a stuffed eagle owl measuring about 70 centimeters in height using a 3D scanner and to produce it as a tactile model for blind visitors using 3D printing. Another extraordinary example of an external order was to printing a copy of the relic of our city's patron saint. The City Museum of Düren wanted this as a tactile model for blind visitors in original size. Due to this size, we had to split the model and print it in several stages. The largest model part then also required the longest printing time we had ever achieved in our institute. The printing took 6 days non-stop, interrupted only by short material changes. These diverse tasks also required us to use other 3D printing processes to achieve the desired result. In addition to 8 FDM printers, our company now also has 5 SLA and 2 SLS printers. While FDM printers apply the hot plastic in thin layers, SLA or stereolithography printers work with liquid polymers that are cured by laser or LED light. SLS or selective laser sintering printers fuse fine plastic powder by heating or sintering in technical terminology it with a laser. However, there is one principle that we follow very consistently. We do not produce tools that could land us in legal and product liability difficulties. This implies that we do not produce any parts that could be attached to medical aids, such as white cane, walker or wheelchairs, and thus affect safety. Even though 3D printing offers many opportunities, it must be admitted that there are also limitations, and not everything can be produced with 3D printing. Even if the coverage in the media gives that impression, it is important to correct some stereotypes here. In any case, it must be clear that only FDM printers require only a few additional devices and space for placing the printer. If you switch already to SLA printing, you need good ventilation and a wet workstation, as you will encounter evaporation of the liquid polymers and the isopropyl alcohol which is needed for cleaning. In addition, it already requires some protective work equipment such as nitrile gloves and face masks. Operating SLS printers is even more complicated. Although they do deliver components made of polyamide in industrial quality, the machines require a significantly higher financial and material investment. The smallest version of such printers start at around 14,000 euros. In addition to the printer, you also need sieves and sandblasting equipment for post-processing the models. Due to the microfine powder, more elaborate personal protective equipment is also required. It is therefore likely that FDM printers will mainly be used in a price range up to 9,000 euros for our purpose. These are relatively easy to use, require little space and few additional technical accessories. In addition, materials research is enabling the development of increasingly high-performance plastics and composites as manufacturing materials. This brings us to one of the main limitations. The choice of material is essentially limited to plastics. If you have to make components out of real wood or metal, you have to rely on traditional manufacturing methods. Of course, it is also possible to have components designed using a CAD manufactured in metal by one of the numerous 3D printing service providers. But however, the production of these components in a service provider is expensive and can take several days to weeks. The advantage of rapid prototyping is consequently lost in this case. However, an essential aspect that is indispensable for the effective use of 3D printing and prototyping is the ability to develop models digitally using CAD software. Of course, this is not rocket science for most of the tools we are developing as aids for our visually impaired customers, but at least it does require some time to familiarize yourself with the software and develop appropriate skills. Therefore, platforms such as tactiles.eu are an essential aid to obtaining appropriate models for the target group without designing for yourself. A further advantage of this platform is not only the possibility to download such models for free, but also that these models have been developed by practitioners and thus guarantee the functionality of the models for the target group. Once downloaded, the model files have only to be converted into a file using a special program called Slicer. This file describes the model in layers and controls the printer with the corresponding device parameters, such as temperatures, print speed, and flow rate of the plastic. Thus, no design knowledge is required. You just have to be able to operate your printer and the Slicer software. There is also a useful online tool for creating location maps called TouchMapper. Using the free map material OpenStreetMap, you can easily create a 3D model by entering an address. The result is a file that can be prepared for 3D printing in the Slicer and create a tactile map. Summarizing our experience with 3D printing, I can say that this technology has enabled us to continue creating tactile models and maps after the departure of a colleague. The technology allows for many variations of prototyping, but is limited to plastic materials. However, 3D technology offers a quick start in development of prototypes for all educational institutions for visually impaired people that do not have a workshop or skilled technical staff. Thanks to the availability of online platforms for purchasing tactile 3D models, it is not absolutely necessary to develop certain tools yourself. Due to technical developments, efficient 3D FDM printers are already available and affordable from 800 euros upwards. So there is no reason to wait any longer. Be courageous and give it a try. If you like this podcast, I kindly ask you to subscribe. Our next podcast will be published in a few days before the Christmas break. So stay tuned and goodbye.
Funded by the European Union. Views and opinions expressed are, however, those of the authors only, and do not necessarily reflect those of the European Union or EPOS VZW. Neither the European Union nor the granting authority can be held responsible for them.